Let's review some things about eigenvectors and eigenvalues. And in particular, why is it that we need to talk about complex numbers when we talk about eigenvalues? So what is an eigenvector exactly? Well, let's say we have a vector in 3D space, and for simplicity I'm going to consider the vector to be a unit vector along the z-axis. Now what I'm going to do is I'm going to make this vector, and you can see it in the image here with a red line, and let's say the dot points in the direction of the vector. What if I rotate my perspective by 30 degrees around the z-axis, which means I view the same vector but rotate the axis by 30 degrees, or I just turn myself around and try to view the vector from an angle of 30 degrees. Do you see any change in how the vector looks? This time, let's consider a unit vector along the positive x-axis. And again, let us shift or rotate a view by 30 degrees around the z-axis. Do we see anything changing about our view of the vector? So here again I have my vector pointing along the positive x-axis, and the way you can see that from this image is that I have this tiny little dot here which is pointing towards us. Now as you can see, the only way that this dot comes back to a configuration when we rotate about the z-axis, the only way that this dot comes back to the configuration where it's again pointing towards us is when I rotate this vector about the z-axis by an angle of 360 degrees, and that's the only way. Any other angle of rotation, we see that the vector sort of shifts the dot kind of starts pointing away from us. And what this hints at, what the kind of hint this gives us is that somehow rotations about the z-axis by arbitrary angles will not bring back a vector of the form which is originally pointing along the x-axis or lying along the x-axis. It will not bring back this vector into its original configuration except for very special choice of angles, which in this case happens to be 360 degrees. Let's make this idea a little clearer in the next slide. So what we've observed, at least qualitatively, is that a 30-degree rotation, for instance, and 30 degree is, I'm just taking that as an example, a 30-degree rotation of a vector about the z-axis will leave the vector unchanged if the original vector is already pointing along the z-axis, which makes sense. However, if the original vector is pointing, say, around the x-axis or the y-axis or some other direction, and if I rotate this vector by, say, 30 degrees around the z-axis, or if I change the underlying coordinate system, I rotate the coordinate axis by 30 degrees or some other angle, our perspective, our view of the vector will change. Therefore, there are, given an operation, given a transformation like a rotation transformation, and in this particular example the transformation we are talking about is a rotation about the z-axis. So given such a transformation, it's possible that there are some special vectors which remain unchanged when we apply this transformation on those vectors. For instance, if I have an original vector pointing along the z-axis, as we've just seen in the animation, and I apply a rotation transformation about the z-axis on a vector which is already pointing in along the z-axis, the vector will not change. And such special vectors are called eigenvectors of the corresponding transformation. So let's look at this more quantitatively in the next slide. Now, when we perform a transformation, and as we talked about just now, that there are certain special vectors which remain unchanged, it's possible that those vectors still pick up what is called a scaling factor. And by a scaling factor, all I mean is that if the original vector was, say, pointing along the z-axis, after the transformation, the vector will still point along the z-axis, but it might become longer or shorter. That's one example of scaling a vector. Now let's look at the rotation matrix for an arbitrary rotation about the z-axis. This rotation matrix is very similar to a 2 by 2 rotation matrix which we have discussed previously in some of our videos, except that instead of it being a 2 cross 2 matrix, it will be a 3 by 3 matrix, and we have added one more column and a row with a diagonal entry of 1 in the last 3 cross 3 element, which is as you can see on this particular slide. Now so this is again in the basis where you have x coordinate represented by a column vector 1 0 0, y coordinate would be 0 1 0, and the z coordinate or unit vector along the z axis would be 0 0 1. So if I take this rz theta, which is a rotation by an angle theta about the z axis, and apply it to a unit vector which is pointing along the z axis, which I represent by z hat, you see that this transformation gives you back the same vector, and it picks up a scaling factor of exactly 1 units, so it doesn't change at all. But this pay factor, this 1 which you see on the right hand side of the equation, is what we refer to as the eigenvalue of the equation. So if I have a transformation like the rotation matrix we see on the slide, and this transformation has special vectors called eigenvectors, in this case z hat being an eigenvector, then the relation you see on the last line, the equation that you see on the last line here, is called an eigenvalue relationship, where the matrix which represents the rotation matrix gets operated on the unit vector z hat to give us back z hat with a scaling factor, and that particular scaling factor is called the eigenvalue of the corresponding eigenvector. Now just as a quick check, let us apply the same rotation matrix, which is a rotation by an angle theta about the z-axis, and let's apply this to a unit vector pointing along the x-axis, which is x hat, which I represent by x hat, and that can be represented by a column vector 1 0 0. So if I do this transformation, if I apply rz theta on x hat, what I get on the right hand side is no longer x hat. The right hand side is cosine theta as the first entry, sine theta as the second entry, and 0 as the third entry. And as you can guess intuitively, this is nothing but a vector, again a unit vector in the xy plane, which makes an angle theta with the x-axis. And this makes sense because in a way, whenever we were studying two-dimensional rotations or rotations in the xy plane, we were assuming that this kind of a rotation is like a rotation about the z-axis when the angle theta is measured, say, about the x-axis. So what we end up finding in this relationship, or from this relationship, is that unless theta is 2 pi, which is 360 degrees, or theta is just 0, which is no rotation at all, the rotated vector represented by the column cosine theta sine theta 0 is no longer the same as the original x hat vector. It's only when, say, theta is 360 degrees that cosine 360 degrees is 1, sine 360 degrees is 0, and so you end up getting x hat. So only for those special values of rotations can we say that this equation is an eigenvalue relationship, but it's only for those special cases. And so typically what we'll say is that rz theta as a matrix or as a transformation will not have x hat as its eigenvector, except for these very, very special choices of rotation. And this raises the question that given a matrix or a transformation of the form rz theta, is there a way that I can find out all the eigenvectors and their corresponding eigenvalues? Well, it turns out that that's exactly possible, and the way we do that is we require to satisfy an equation where rz theta operated on an arbitrary vector, which I represent as a column vector with entries a, b, c, should return us back the same vector, except that we might pick up a scaling factor, which I have represented by the symbol lambda in this case. Now how do I solve this equation? Well, one of the ways you can solve this equation is that instead of writing lambda as it is, let's assume that lambda is getting multiplied or is multiplying an identity matrix, because lambda is the same as lambda dot an identity matrix, and in this case, since we are working in a 3 by 3 vector space, we can assume that it's operating on a 3 by 3 identity matrix. Given that, I can go from the equation that I've written in line 1 to an equation in line 2 where I've replaced lambda with an identity matrix with diagonal entries all lambda. I can solve this equation, and the way I can do that is I can take the right hand side to the left hand side, and I can take the difference between the two matrices since they're both operating on the same column vector ABC, and that leaves us with the equation that you see on the last line here. Now the way we can solve this equation is to solve for the choices of lambda which ensure that the matrix which we have represented as cosine theta minus lambda with the first entry, cosine theta minus lambda as the second diagonal entry, and 1 minus lambda as the third diagonal entry, and then minus sine theta and sine theta on the off diagonal elements, which are the only non-zero elements we have, is that this matrix when applying on a column vector ABC gives us 0. Now how do I ensure that that is always possible? Well, let's look at that in the next slide. So if you give this equation some thought, it turns out that, let's say I represent the complicated looking 3 by 3 matrix with lambdas being subtracted of the off diagonal element, or rather the diagonal elements. Let's represent that matrix with the symbol M. Now if I have an equation of the form M operating on the column vector ABC, if M is an invertible matrix, I can perhaps multiply this equation M ABC equal to 0. I can multiply both sides of this equation by the inverse of M, right? And that will give me something like M inverse M operating on the column ABC to again give me 0, because if M inverse multiplies the entry 0, you'll just end up getting 0. But if that is the case, we know that M inverse times M is nothing but the identity, and if we have an equation of the form that identity is getting operated on a column of the form ABC to give me 0, the only way that this equation can be satisfied is for all of ABC equal to 0. But that would mean that the column vector that we were looking for as an eigenvector of the equation RZ, or rather of the rotation matrix about the z-axis by an angle theta, that column vector ABC will have all entries 0, which is really just a very trivial solution, because that's no solution at all. It's just dealing with not a vector at all, but a point which is a equal to b equal to c equal to 0. So for us to have a non-zero solution to this equation, what we explicitly want is that the matrix M should be non-invertible, because if at all it is invertible, then the only possible solution is that we do not have any eigenvector. So the way we ensure that a matrix is non-invertible, and sometimes that's also called singular, is for the determinant of that matrix to be 0, because a matrix whose determinant is non-zero can be inverted. So if the determinant, if we can ensure that the determinant of matrix M is equal to 0, it will ensure that the matrix is non-invertible, and then we have a shot at figuring out the choices for ABC which are non-trivial, which are not all 0. Thus, what we end up finding is an algebraic equation which we obtain by writing out explicitly the determinant of the matrix M, and what we end up finding is that this algebraic equation which you see on the last line should be equal to 0. We should be able to solve for this algebraic equation. So let's see how we do that. So if I try to solve this algebraic equation, and what are we really solving for? We're solving for the lambdas. We're solving for the eigenvalues, and as long as we have non-zero eigenvalues, we are able to go back and find non-trivial eigenvectors. Now if I try to solve this equation, you see that one possible solution is that lambda equals to 1. And for the rotation matrix, which is a rotation about the z-axis by an angle theta, we have already worked out just intuitively that when lambda is 1, the scaling factor is 1, the corresponding eigenvector is just a unit vector along the z-axis. However, this also gives us two other solutions. Now notice that this is a cubic equation in lambda. It's an equation of order or degree 3. If I solve for the other two roots, it turns out that those roots are complex numbers. The first of that complex root is cosine theta plus I sine theta, which, if you know the Euler's identity, is equal to e to the power of I theta. And the second complex root is cosine theta minus I sine theta, which is the conjugate of the first complex root. It turns out that for an eigenvalue relation, or for us to be able to solve eigenvalues of a transformation of the kind of transformations we are looking at, we do require to introduce complex numbers into the picture. And that is because this was a specific case where we worked out a 3x3 rotation matrix about the z-axis. But in general, say I have an n cross n matrix, and I want to find out the eigenvectors of that matrix. If I follow the same procedure, the logic remains the same. What we want is that when this matrix operates on a column vector, we end up with the same column vector up to a scaling factor lambda. And again, if I want to solve for this equation, I want to ensure that matrix, n by n matrix minus an identity matrix multiplied by lambda, when operated on the eigenvector, should give me something which is equal to 0. And that will necessarily require for this matrix to be non-invertible. And so at the end of the day, solving for the eigenvalues reduces to an algebraic problem where we have an algebraic equation of order n in the eigenvalues that we're looking to solve. And by the fundamental theorem of algebra, any algebraic equation of this form always has roots as long as we work in the complex plane. And therefore, that leads us to the crux of this particular video, that eigenvalues necessarily require the use of complex numbers. What do they really mean in physical situations? When is it that they are permissible? That's a different matter altogether. But whenever we are solving for eigenvalues, and by construction from there trying to find out the eigenvectors, it turns out that we need to be able to introduce complex numbers into the picture. So hope this was of some use and as a good refresher to how we go about finding eigenvalues and eigenvectors. We haven't explicitly worked out eigenvectors, but if you know the eigenvalues, you go back and plug it into the eigenvalue equation that we worked out, we'll be able to find out the eigenvectors as well. So hopefully this was of some use. Let's continue our discussions. Thanks.